Hello.
Hey, Pamela. Oh, I'm not on the headphones. There, much better. Hey, how's it going?
It's going okay. I'm working on trying to find all the things that are slowing my computer down, though. So there's going to be a little looking around for a minute.
Enjoy. And in fact, my daughter is trying to find me. Hold on one second.
We're sorry, Internet. Apparently, we went live just as we realized we weren't ready. I am just back from a trip, and I left code running on my computer that is still running. I've been running this software for days now. And so I can't reboot, and so I'm just killing individual processes.
Oh, good. Yeah, sausage getting made. Watch it.
Yeah.
I just got back from ComSciCon, which was a conference in Boston. It was organized by the folks that do Astrobytes, and it was a great time. I had a really good time. So if anyone from ComSciCon is watching this or listening after the fact, hello. And I had a really good time.
And I just got back from the Maven New Media Workshop. So apparently both coasts had workshops going on teaching people how to be better science communicators. So hello to any of you that were at the Maven New Media Workshop.
And it looks like we're going to do a fourth episode of the Hangout with New Horizons, and that's going to be next week. Yeah, it's going to come really quickly. So once we've sort of settled on a date, I'll let everybody know. But yeah, we're getting close. We're just like 2.5 weeks, 3 weeks away from seeing Pluto for the first time close up.
So I have to admit, I'm kind of annoyed that Ceres isn't getting as much coverage as Pluto, because Ceres is proving to be way super awesome, cool with unexpected, and it's a super cool object, and it also used to be a planet. So I'm Team Ceres.
Oh, Ceres. Ceres is so last month. No, have you seen that new mountain? Have you seen that new mountain?
Yes.
Series? It's crazy.
This is what I'm talking about. We have weird reflectivity. I actually, the most humorous crank email tweet I've ever gotten from someone who thinks that it's not a highly reflective place, but actually that Ceres is internally illuminated, which was novel. But anyways, we have these massively shiny spots. We have unexpected mountains. There's hills on it. This is something that is geologically totally planet-like, which is totally unexpected. And we're never going to get the data from Pluto that's going to allow us to make the kinds of discoveries that we're going to make with Ceres. And that team is like getting no press coverage. And
they're getting tons of
awesome
coverage. I mean, and
not like Pluto though.
Yeah, but the trick is that, when you stretch it out, right? Dawn is going to be orbiting Ceres for years, and it's going to be delivering tons and tons of science just ongoing. But this flyby of Pluto, it's one shot of the science, and then that's it. So don't worry. Ceres will get its love in the long run. So hey, this is not just me and Pamela hanging out talking about space. This is apparently an episode of Astronomy Cast. So clearly your computer is bogging right down, by the way, Pamela. I can tell that it's freaking out. So I'm going to say hello to a bunch of people who are sort of in the Q&A app. So I'm going to say hi to Guido Bibra, Richard Clark, Cecil Morgan, Odin Faborg, Amir Liv Baron, Nancy Graziano, and Peter Waldman. So hey, folks, welcome to this very special episode of Astronomy Cast that we're doing on a Tuesday because Pamela was traveling last week, and you're going to be traveling again next week, right?
Yes. So we will be again next week doing our episode on Tuesday. We want to make sure you get all the science, although we are taking August off.
And July.
In the interim. Yeah, we're taking most of July off.
How many more episodes do we have before we go into hiatus? One,
I think
right?
We have two, I think. 2?
Okay. All right. That's fine. I'll go 2. And same goes for the weekly space hangout. So I think we've got 1 or 2 more episodes of that, and then we're off till Labor Day, after Labor Day, because you're going to be at Dragon Con, I'm going to be at PAX, and Yeah.
So join us on the coast of your choice.
Yeah. Yeah. Pick one, whichever one you want. If you're going to go to PAX, look me up. We'll go hang out. Okay, cool. Well, let's do this show thing if your computer has stabilized.
Let me kill Safari and email.
Not email.
Sorry.
Not email.
Well, I do all of my business accounts.
Oh, I can see your email really fought back.
Oh. Huh?
I guess I'll make a quick announcement, which is for anybody who's watching this right now live. If you go to the WSH crew, I posted, we're looking for a suggestion on a topic to do for episode 200 of the Guide to Space. So I put a post there, and I'm giving away one of my meteorites. So to whichever topic we decide that we really love, and we're going to choose that. So still got some time. Go into the WSH crew community. You might have to join it if you're not already a member. There's a post there for me, and suggest some topics for us to cover for that episode. And whichever one we choose, you'll get one of my chunks of space metal. So more incentive.
Okay.
And
I think
You think you're ready? You think you've shut down every single thing on your computer?
Well, no, because I'm still talking to you. So clearly Chrome is still open. But I'm down to Chrome, recording software, and the program I've been running in the background for a week that I refuse to stop until it's done executing.
Okay. Awesome. All right. Well, let's do this thing we like to call Astronomy Cast.
Sure.
And so once again, we'll take about just shy of 30 minutes to do the show, and then we'll stick around and answer your questions about space and astronomy. And for the people in posting in the Q&A that you might want to delete your comments, that's probably a good idea now that I've said hello. So if you've got any, I'm going to say hi to Sylvan Westby as well. But now if you want to delete your hellos, that would be terrific so that I can just see the questions. All right. Let me know when you're ready.
I think I'm ready. I hope I'm ready.
I have pressed record.
It's recording in mono. I did it right. Hi, Yay. Preston.
Okay, let's go. Astronomy Cast, episode 382, Degenerate Matter. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of Cosmic Quest. Hey, Pamela, how you doing?
I'm doing well. How are you doing?
I'm doing great. So we are now 2 episodes away from hiatus. So
something like that.
Yeah. So there'll be this episode. This is the penultimate episode.
And the time that we're spending on hiatus is actually going to be spent doing lots of awesome things that you can follow along with online. Fraser is continuing his coverage of New Horizons over at Universe Today, and with his weekly video series, I'm doing the same thing over at CosmoQuest, and I'm also covering Ceres because I'm Team Ceres. So expect lots of asteroid coverage coming up in the next month. And in August, I'll be over at the International Astronomical Union meeting in Hawaii, basically following all of the politics of our field as we work to define and refine our understanding of the universe and how we name things, because this is apparently a thing to argue over.
Yep, you're going to decide that. But Pluto, the vote for Pluto is not back on the block this time,
it's not. No. Pluto, there's a lot of rumors going around that somehow Pluto's going to get redefined. No, that is
not going to happen.
No, it's really not. Anyone who is making a claim that Pluto's a planet, one thing to ask yourself is, have they written a book, or are they in a position to monetarily benefit from making a big deal about how Pluto should be a planet? Because that seems to be what it's often tied to. Because if you're just interested in the science, it really doesn't matter.
Okay, well, let's get on with the show. So in some of the most extreme objects in the universe, white dwarfs and neutron stars, matter gets strange, transforming into a material that physicists call degenerate matter. So let's learn what it is, how it forms, and so on. All right, Pamela. So you put this topic in the list, and I'm amazed that we haven't actually. I guess we've done it separately, but we haven't actually focused on the degenerate matter itself. So, what is an example? Like, what is degenerate matter?
I think the most simplistic example is your friendly neighborhood white dwarf star. This is the eventual outcome of our own sun. It's mathematically the easiest example to understand. And it's basically a case where you take a star, like our sun, and you stop generating light in the core. And when this happens, you no longer have an outward light pressure to counterbalance gravity's desire to crush that star into an itty bitty little tiny piece. So when the light shuts off, the star begins to collapse violently. As it collapses, the atoms crush together, and you end up with the material basically supported with the electromagnetic force combined, so that the protons are pushing out against the electrons going, no, we shall not combine. But as they pack as closely as they can possibly pack together without combining, the electrons have to assume a almost crystalline state. Physics. My recording just stopped.
Yeah. Do you want to try starting it again?
Yeah.
I'm just going to leave my recording going, and we can just sync up again.
Yeah. Trying to figure out why it says too many real instruments are recording. There's something on my computer that's eating bandwidth. Or
maybe turn off Google Drive if you're running that, and Dropbox, because those can gobble up your bandwidth.
That's what it is. Dropbox is to the offender. Okay, thank you. Wow, Dropbox is going mad. How do I turn that off?
Well, are you saving this episode to Dropbox, or are you saving it to your desktop?
It's linking photos off of my laptop is the issue. Quitting Dropbox. Okay, I've quit Dropbox. It will stop linking photos. Thank you for mentioning that. That I would not have found.
That has caused me all kinds of problems in the past. I just left my recording going, so...
Okay, I will start that answer over and hopefully be more succinct. Sorry, Preston. This is Pamela. My computer's going nuts. I'm going to start answering that question again from scratch.
What is degenerate matter, Pamela?
Well, degenerate matter is what you get when the whatever particle it is crammed together so closely that it forms essentially a crystalline structure. As all of the different particles make sure that they don't assume the exact same energy state, which means they're in the same energy level of an atom and they have the same spin state in the atom.
All right, we're going to have to unpack this a little bit here. So if I think back to my high school chemistry, my university physics, electrons go at various energy levels around the nucleus.
Yes.
And so you can fill up 1 in the first orbital,
2 in the first,
2 in the first, 4 in the second, and then it goes, all the way up to like 16 and 32 and so on. So those are the orbitals. You've got the electrons all kind of trying to pack together into those orbitals. And if it is degenerate matter, what am I going to see?
So what you're dealing with is actually slightly more complex than what you're saying. Each energy level is actually pretty discrete. So you have what's called the S1 orbital, which is the lowest energy level in an atom, and 2 different electrons can be in it. But they can't have identical quantum numbers. This means that because spin is a nice and easy to change quantum number, one will be spin up, one will be spin down, so they're not identical. So they have the same energy, mostly. The only difference is in the spin state to prevent Pauli exclusion principle, 2 things from having the same quantum numbers. In the next set, you have the S2, which again, you jam 2 electrons in, they assume different states. Then you have the D and the P orbitals. You keep adding, and they have different probability functions for where around the atom you're going to find these orbiting electrons. Now, when you're in a degenerate star, you don't have the space for every atom to have its own infinite set of energy levels. And in fact, you run into the situation where you have two atoms crammed right next to each other, and the electrons are trying to share energy levels, which means that you can't have both atoms have their electrons in that same S1 orbital with their spin up and spin down, because then you're trying to have two atoms sharing the same energy state. So in this crystalline structure, you end up with the atoms spaced out and the electrons forming this cloud of ever-increasing energy levels where things are packed so tiny that in order to not offend the Heisenberg uncertainty principle, because we're all about uncertainty today, things are very, very closely located in a place, because otherwise their energy level is like going to overlap with something else and you have the same quantum numbers and badness occurs. So things are located right in one place. But this means that they have all sorts of crazy momentum, which means you have a whole lot of fluttering about occurring in a very small space as you basically have this insanely high pressure diamond of a star.
And you know, we talked about this, that this is the state that a star like our sun will see at the end of its life, when it no longer has the outward force, the light pressure from the fusion at its core. That shuts off, but you still got the inward gravitational force of all of the atoms that are at the core. But it could have been anything, right? It could be bits of helium, bits of carbon, bits of oxygen. But the point is that when it gets squished together that tightly, it turns into this very special type of matter, because the electrons are not able to orbit as freely as they would like to around their nucleuses, right?
And it's not actually everything that can do this. This is where we get limited to, you have to have this quantum number limitation that causes the degeneracy to happen. So we talk about this most often with fermions. We also can see this in protons, although in things like the white dwarf star that our sun will occur someday in the future, the proton's degenerate effect is basically just an error on the electron degeneracy. We see this with neutrons, however, as well. But we don't actually see the carbon having to worry such that you end up with a carbon degeneracy, because the electron degeneracy and the proton degeneracy, it's the individual particles that we worry about.
So when you see those articles on the internet, and I'll admit that we've done that a bit on Universe Today, about, it's the biggest diamond.
Yeah, totally legit.
Is legit. So it is a diamond, but it is not a diamond that you want to attempt to chip off the white dwarf. And if you could, though, chip off a chunk of white dwarf star and bring it to Earth, would it remain in its degenerate state? Would you have a diamond?
No.
Right.
Well, so you might still have a diamond, because there's nothing to prevent the carbon from staying in that crystalline structure, but you'd no longer have a degenerate atomic mix. So what we have with white dwarfs is to look at our sun someday in the future. Our sun is currently happily having nuclear reactions burning in the center. You have light pressure going out, and it's the light pressure generated by that nuclear burning that is supporting our sun. Turn off those nuclear reactions, turn off that pressure hose of light, outer layers of the sun are just going to collapse down. And while they collapse, initially gas pressure is trying to go, no, stay out, you're hot, I'm hot, let's support ourselves. But the gas pressure can't win. The ideal gas law can't support the star against the force of gravity. So it collapses and collapses and collapses. And what eventually happens is it's, with relativistic corrections, it's the electromagnetic force between the protons and the electrons repelling each other that is holding the star apart to a certain degree. And more importantly, it's the electrons pressing each other against each other, being all degenerate in their separate, no two quantum numbers the same, degenerate gas.
Right. Okay. And so really the only thing that's stopping this star from compressing any further is that each individual electron resists being crushed any further because of this problem.
What is that?
My daughter is making something in the oven, and welcome to summer. This is one of the reasons I like to take the summer off. So hopefully that's not going to happen again, but it probably will. I apologize, Preston. All right, let me take another crack at this.
Okay.
This is just going to be Preston. You're really going to got your work cut out for you today, Preston.
Sorry, Preston.
Okay, so right. So the situation is that the star wants to keep on collapsing. It can't, it reaches the point where really the only thing stopping it is just these individual electrons are just pushing against it, literally with like uncertainty that this is the thing with the Pauli exclusion principle, that just because you can't have them occupy the same quantum state, they don't compress any further. I just find that concept just so fascinating. But of course, nature has figured out ways to get around this problem, which is if you just have more mass, you can just ruin the laws of physics.
Well, it's not that you
exploit new laws of physics.
You exploit new laws of physics. And this is one of those stories in science that kind of just makes you grumpy. So Chandrasekhar, arguably one of the most brilliant and well-organized and thoughtful in terms of how he approached getting everything done, astronomers of the modern era, of the post-quantum mechanics age of astronomy. If you haven't read a biography of this man, do so. The one written by, I can't remember his first name, last name is Mukherjee, is absolutely brilliant and gives you amazing insights in how Chandrasekhar was able to accomplish all the things he did. When he was just either 19 or 20, depending on what source you read, I think he was just 20, he traveled from India to England to attend graduate school. Now, I was 22 when I started graduate school, and I went straight through without stopping, finished everything in 4 years. No, he had to do things on an accelerated timeline. So this very young, very brilliant man had a very long boat ride. And while on this very long boat ride, like many of us nerds, he started playing with the theories of stellar atmospheres. And I have to admit, I have done the same thing. But unlike me, who was just happy to figure out, well, if you do this to a star, this occurs, he actually took things to the extreme and realized that all of the, at his time, modern calculations of stellar atmospheres failed to take into account the needed relativistic corrections when they achieved the highest pressures that occur when you turn off light pressure when a star dies. And when he added in those relativistic corrections, he realized that when the mass of the collapsing object exceeds 1.44 solar masses, the electron degenerate pressure just isn't enough anymore. And at this particular mass cutoff, the electron degenerate pressure gets overcome and the electrons and protons squish together, lots of energy is given off, and you end up with a neutron star. Now, when this happens in the real universe, it happens with great violence, and it's called a type 1a supernova. And you don't always end up with exactly 1.44 solar masses left over when this is all over. In fact, you never end up with that much mass left over. But in other situations where the collapsing star has, during the collapse, what's left over is greater than 1.44 solar masses, you end up collapsing not into an initial white dwarf, but instead straight away right into a neutron star, where in this case, it's the neutrons trying to go, can't share the exact same quantum numbers, and they're pushing one another apart with this neutron degeneracy pressure, trying to support this extraordinarily dense little tiny fragment of a star.
Right, but in this situation, right, the proton and the electron are actually squished together to make neutrons.
Yes.
That all the electrons, all the protons, there's no longer protons, electrons, there are only neutrons. And it's this final stage where the neutrons you can't make two neutrons share the same quantum state that you're left with.
And what's really matter is it just does not. My recording stopped again. Okay, trying this one more time.
I'll just keep on recording.
Yeah. Sorry, Preston, my computer hates my guts. So what's really amazing about this degenerate matter is how it just doesn't behave in a way that we're used to. Normally, you think you add more matter onto something, it physically gets bigger. In normal gas laws, you increase the temperature, the pressure goes up. With degenerate matter, in stars, yeah, sure, they're hot, but white dwarf stars cool off over time. They start out hot because they're a stellar core remnant, but they cool and they stay degenerate because it's the gravity that's collapsing them down to create this huge pressure. A white dwarf, again, goes up to 1.44 solar masses. A white dwarf is about the size of our moon. So imagine our sun, which is hundreds and hundreds of times bigger than the Earth, getting collapsed down to the size of the Earth's moon. That's kind of impressive, but that's nothing on what a neutron star does. Neutron stars are between 1.44 and 3 solar masses, and their diameter and the diameter of Manhattan are about the same. This
right,
means
they're about 10 kilometers across, right?
Yeah, and so if you took a neutron star and set it on Manhattan, first of all, you'd collapse the entire Earth onto the surface of the neutron star, and there would be no more Manhattan or Earth, which would be bad. But if you did this instantaneously, there would instantaneously be this moment of the neutron star just sitting happily on top of Manhattan. Now, in terms that you might be able to think of a little bit better, a teaspoon of white dwarf has about the same mass as an elephant, whereas a teaspoon of neutron star, I'm just confirming that I get all of the numbers on this correct, is 20 billion tons on Earth. So
like a mountain?
That's, I think, a lot bigger than a mountain.
Wow.
Yeah.
Yeah. Well, I'm trying to think what the Earth is. Not the whole Earth. The Earth is like
let me
6 or something 2 septillion tons, I think. But yeah, that's a lot.
Yeah. So the entire Earth is 6 times 10 to the 21 tons, but but the mass of a teaspoon, little tiny amount of neutron star is 2 times 10 to the 10 tons.
Did your recording stop again there?
No.
Okay, good. Sorry, Preston. This is the worst episode. Okay, great. So that just gives us a sense of scale. So we get these neutron stars. They are made of this degenerate matter. But what would it be like? Like, is it, neutrons packed together like crystals? Are they jiggling around like a liquid or a gas? Like, what? If you could take a look at it.
So when we think of liquids and gases, we think of things that have the capacity to flow. This is actually built somewhat into the definition, where in a solid you have atoms that are pretty much locked in place. Their electrons are happily whirling about them. In a liquid, you have atoms that are chemically bound, molecules that are chemically bound to one another in such a way that they form a continuous medium. Happily non-attached. Starting that sentence over.
Crashed again.
Yeah. Okay. We are recording again. So in a liquid, you have atoms that are still somewhat connected to one another, although these connections are, fluid. In a gas, things just are kind of flying all about. That's the definition of a gas. You don't even necessarily have collisions on a regular basis. In a neutron star and in a white dwarf and in any other form of degenerate matter, you don't really have motion other than a frenzied vibration. The Heisenberg uncertainty principle has basically located very, very precisely where everything has to be, because if it moves, it's probably going to end up overlapping its energy level with something. So you be in that energy level right there, don't move. You be in that energy level right over there, don't move. But since it's really well, you can't. Okay, starting that sentence yet again. So with what this means is, since you have really located things in place, you can't know how fast they're moving, which means these little suckers are like vibrating or vibrating is probably too specific of a term. They're being frenzied in a very little tiny space. So you have lots of frenzied activity in very tiny spaces, and it's not a function of temperature in these high pressure environments, which is just counterintuitive to how we ever think of gases.
And so is it like literally at the very limit of the Heisenberg uncertainty principle? Like you just can't get any more certain than this? This is as certain as nature. Like it's almost like your certainty is approaching infinity, and that any more certain and the whole thing just collapses into a black hole, because it's just got more, the more gravity you get to the point that it's just trying to mash the thing together even further, it kicks over into a black hole. And that's the next step, right? As we get black hole.
And I don't think I'd go as far to say as we're at the limit of the Pauli exclusion principle or the Heisenberg exclusion principle. It's actually much more complicated than that. But we are at the limit of what the degenerate gas pressure can support. And when the degenerate gas pressure, with all of the factors, including relativistic corrections, when all of that is put together and mounted against the of gravity, I'm really sorry, Preston. I will never again set important scientific code running on the computer I use for recording. Okay, so when you get to the point that degenerate pressure is, I'm going to restart GarageBand and see if that helps.
All right, I'll just keep recording.
I'm really sorry, audience. Oh man, I ran it on my home computer because the power at home is more stable than the power on campus. But there was clearly a flaw in my logic.
Is there no way you can even pause the process? You probably don't want to.
Yeah, Okay, trying again. Okay, so when you get to the point that you overcome how the degenerate pressure is able to fight against this onslaught of gravity crushing down, we actually reach the point beyond neutron degenerate pressure that we're not entirely sure what's going on. There are people that run maths claiming that you end up with a quantum degenerate, or quark rather, degenerate pressure, where the quarks are now the things that are trying to find ways to not having identicals. But at the same time, we have no way of proving that. There are people that even go so far as to make up particles that supposedly make up quarks, even though we have absolutely no need for particles that make up quarks, or any evidence to support the need for particles that make up quarks. So basically, you reach a point where people start making up shit. What we do know is, beyond neutron degeneracy pressure, things collapse down, you get a black hole, and we have no clue what's going on inside the event horizon. Full stop.
Full stop, right. And so on the one possibility, you've got a situation where there is some other state, but it's within the event horizon of the black hole, so we can never see it. Like, as you said, quark degeneracy pressure, although it's possible that we could maybe try and figure out, we try and see if there is a quark degeneracy pressure using some super advanced Large Hadron superconducting, super awesome collider in
well,
the future.
But the problem is, how do you contain that in a stable, non-explosive way? Which is, I mean, what you really need is to compact them using magnetic fields, but we haven't figured out how to pack enough energy for a prolonged period to, either with lasers, you could also do it with lasers, with either lasers or magnetic fields, crush something in the appropriate way. With lasers, we can create the needed pressures, but for, I think it's either pico or femtoseconds.
Mm-hmm. And the problem being that if you can compress those things into that size, you get a black hole, which then it is necessarily behind the event horizon, and then the thing will evaporate again, and then you won't know. But maybe, maybe there's some way that a black hole will evaporate in one way if the quarks are mushed together, and maybe they'll evaporate. Anyway, this is not our problem. The point being, we don't know, and we kind of right now kind of can't know. And it could very well. So what you're saying, right, is there could be stages inside. It could go, you end up with a black hole that is 20 times the mass of the sun, and inside it reaches a certain size, and then ones more than that compress further down until they reach whatever is the subatomic particle that makes up quarks, and then maybe that remains. Or it could just be that it's just continuously compressing down forever. Which is, I love this idea.
That's where we get to the concept of the singularity. Yeah. And people just love to talk about that. And this is why we study science, is we still have big questions we don't know the answer to. But there is one thing that we have totally left out, because it doesn't exactly crop up in astronomy that often, and that's the low density, totally creatable on Earth, cold creation of degenerate matter, which is what happens with Bose-Einstein condensates when you get things cold enough. As you get the atoms colder and colder and colder in this single atomic variety superfluid, all the electrons are like, must go to the lowest energy level, except if all of the atoms in the material are all trying to assume the exact same energy level, you can't do that. You can't get there from here. And so you end up with really weird stuff happening, like as you cool and cool and cool and cool a container of stuff, the stuff will actually quite politely climb out of the container as the atoms try to spread out to electrons to have the same energy level, but in different places.
I love this idea. We've done an episode about absolute cold, and I think that's what our next week's one is. We're going to talk about getting to absolute zero. But the method that they use to cool down atoms is, I always sort of envision it like someone's on a swing, right? And then the person comes back on the swing, and then you absorb their momentum from the swing each time they get closer and closer and closer, until you've sort of got them as stopped as you can. And so they shoot lasers at these atoms and try to sort of move them in ways that the opposite of the way that they're trying to jiggle, and that keeps the whole thing down. And you get all of these atoms together, and then, as you said, they negotiate almost their quantum states, and then the whole thing just starts to move like one big entangled quantum state. It's really interesting, and we're going to talk about this next week because it's such a fascinating thing. So I think that was a great segue, and I am going to wrap up this week's episode, and we will continue on with the conversation about this other way to get to incredibly extreme exotic matter using cold as opposed to pressure.
And I really hope that my software will be done running by then, and it will be a much more pleasant recording.
That sounds great. We'll talk to you next week, Pamela.
Have to restart the episode to say goodbye. Hopefully it'll be a much more pleasant recording of the episode. I'll talk to you next week, Fraser.
Please put a bullet in
the
that
recording. Oh, God. Thank you for all your patience, dear audience. We love you. I don't love my computer at the moment.
Doesn't love you back.
No, it's kind of mutual. I'm having a Monday, even if it's called a Tuesday.
Okay. I am saving. Then I'm going to put it in the Dropbox. Then I am going to wash my hands of this whole thing. It's Preston's problem now. Poor Preston.
Oh. While you do that, I'm going to restart Chrome and see if that helps.
Okay.
I'm going to first save the link into this Hangout.
All right. So if you weren't aware, you're watching this live episode of Astronomy Cast, go ahead and put any questions that you want into the Q&A app. You can see that wherever you're watching this, it just says we're interacting. Astronomy Cast is interacting live with the audience. Click that, brings open a window. There's questions there. I only see a bunch. We'll tear through these in just a heartbeat. So give us your questions. And it doesn't have to be what we just talked about on the show. I see that there are dozens, nearly 100 people watching right now. You must have a question for us. Anything. Do you want to talk about Pluto? Do you want to talk about Sirius? What are those white spots on Sirius? We don't know. If you don't ask us, we won't tell you. So now's your chance. All right. So Odin Faborg asks, as a star gets hotter, it turns more blue. Could a star get so hot that we wouldn't be able to see it in visible light?
No, because it's black body radiation, which means the peak of its light will be off where we can't see it with our eyeballs. And that actually happens. A lot of the stars in the Orion Nebula that we're looking at in the trapezium, they put out their maximum light in the ultraviolet. Totally can't see it when you're looking through your telescope. But with black body radiation, the light comes out in this whole distribution of colors. And most of the colors that we see with our eyes are totally going to be bright, 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 bright with these blue stars. The entire curve of the intensity goes up as you increase temperature. There's a really great simulation of this. If you Google Nebraska Applet Project black body radiation, you can play with the temperature of a star and see exactly what happens to the colors of radiation it gives off.
Yeah, so even though the star is bright, it looks more bluey. Really, there's just a mountain of X-rays coming off of it, some gamma rays even.
Not so much those, actually. Not
only when it's supernovas. Yeah, okay, but X-rays coming off of it, lots of ultraviolet radiation. But the point is that there's always going to be enough of just all the other colors of photons that you'll still be able to see it. Lots of red, lots of blue.
Infrared.
Even green, and yet there are no green stars.
That's because our eyes fail to integrate light to see green as a peak wavelength. Instead, we perceive it as white because it's halfway between blue and red.
Let's see.
My brain is filled with useless information.
So Ed Thompson asks, since you mentioned the Sirius and Pluto mission at the beginning of the show, what would you like to see explored next? Could be unexplored or already explored.
I'm really excited about the Google Lunar X Prize teams that are planning to send rovers into the caves on the moon. I want little baby rovers to go into caves on the moon and Mars and see if we can find, well, especially on Mars, but I think we need to prototype the technology on the moon. I really want to start, well, first of all, caves are cool. Caves on the moon are awesome.
Yeah.
Caves on the moon are potentially someplace to go live. Let's go figure out if we have a pre-built habitat waiting for us. With Mars, once we've perfected that cave diving technology on the moon, we have the potential to not just go find someplace to stick humans in the future, but there's the potential on Mars where you're protected from the sun's radiation, where you're protected from a lot of other stuff. There's the potential to, well, find dripping caves that have maybe even life still in them, or at least more recently dead life than you'd find on the surface.
Yep. I would like to see, let's see, I'd like to see, I would like to see a rover down on the surface of Ceres. I would like to see a rover on the surface of Venus. And I know that sounds crazy, but there's some interesting technology, some interesting ideas. This idea of a Stirling engine. So it runs like a super hot engine, but you would kind of run it in reverse. And so it would attempt to withstand the temperature of Venus and keep the core instruments safe while you do that. So I would love to see a rover. And even if it doesn't last, like all of the landers that have gone to Venus, they all lasted in the matter of hours. But even if you get something that lasts in the matter of days, maybe weeks, and still is able to send back some more interesting science about the surface of Venus. I mean, we want to know about the geology of the planet. We want to know more about just like what put it into this state, and just to have, like, is it still volcanic? You know, if you could test some of the rocks and see if there's still volcanic gases in some of the rocks, you'd be able to know what the state of it is. So there's a ton of unanswered questions about Venus that I would love to know.
So better than that, there was actually a proposed Russian mission that I heard about back in 2010 and haven't heard about it since. So I don't know if it's still on the table, where they were basically going to throw lawn darts at Venus. They had all of these little spiky bits filled with sensors that had an antenna and something else that came out of the top. And so you can imagine systematically throwing lawn darts at Venus to sample the full width and breadth of its geology as these things plunge through the atmosphere. They're tiny, so they're not going to have a whole lot of camera power, but by having a lot of them, you can explore a much greater region than you can explore with just a rover that you're literally dropping blind onto the surface.
I like that idea. I mean, the great thing about Venus is that it does have a thick atmosphere, incredibly thick, so you don't need to make a very complicated landing system, right? It can just be a simple parachute, and it'll take it all the way down to the surface of Venus. It's really, can you keep your dart, you know, the dart shape will help you get down through the atmosphere as quickly as possible before the heat kills the probe. So I think it sounds like a great idea. I would like to see Enceladus. I'd like to see a lander hit the southern pole of Enceladus and try to get into the ice geyser area. I'd like
you
to
want to kill it with smallpox.
I do. I want Enceladus to be infected with our germs. Okay, let's move on. So Amir Lived Baron asks, has degenerate matter of any sort been created on Earth? Can be studied in a lab, perhaps using some analogous effect? So I think we kind of got at that question. You can create it one way with extreme cold. You can create it another way by using lasers to smash things
and
together.
I don't think they've done that in a sustainable way, that the particles didn't just happily collide together and form things that we could study. But yeah, on the cold side, we totally do that. You can do that in an undergraduate lab.
Yeah, that's awesome. Okay. Michael Jobin says, question mark? That's it? That's your question?
We need more words, Michael Jobin.
And Amir also asks, so what state are the nucleons of a white dwarf? Do they form separate nuclei, or they are densely packed together like the electrons? If it's a former, what elements might there be? So
the protons are degenerate, or the nuclei if it's a carbon. So you have, actually, it would never just be straight protons. You have, I believe, hydrogen helium white dwarfs, and you have carbon white dwarfs. So depending on what the primary atom is, if it's a carbon white dwarf, the carbon is going to pack into a crystalline structure similar to the structure you see in diamonds, except more dense. Grab a tablespoon of it, it's going to spring back out, still be the same structure, just less dense. But if you have the non-carbon white dwarf, clearly it's going to be a crystalline structure of whatever the other material it's made of.
All right, here you go. Michael's got his question. So why do we still have racism, and could that be why science suffers?
Yes, I don't know why we still have it, but there's a lot of research showing that when you increase the diversity of the group, because of the variety of different cultures, ideas, thought processes, experiences, everything benefits. Science is a creative process, and you need to bring all that creativity to the table to move things forward. Chandrasekhar, young man from India who fought amazing difficulties moving to England. I don't think it's any different today. I mean, people no longer make fun of you if you're vegetarian, but not a lot else has changed. And so we really need to work to get, if you think about it, science is majority white men. There have been one Native Hawaiian who got a PhD in astronomy, full stop. Very few of people of color in general have ever gotten PhDs in astronomy. Women are doing better. We're holding steady at making it through the system at, well, those who keep their jobs are 7 to 11%, depending on where you look. Yeah, we need all those voices for science to improve. And what we need more than anything, for people in positions of power to stop being the sources of the hate, for the people who are in positions of power to stop being the justifying force for young people to continue to be racist, misogynist, hateful against everything.
But you definitely can see, you know, more and more of the younger generation not be willing to put up with a lot of this stuff, a lot of the, you know, I mean, anti-gay hysteria 10 years ago, 20 years ago, a lot of that has gone away. You know, anti-trans, you know, I think there's a lot of mindsets that are changing. And I think the internet is a big part of this. I mean, the internet, as we've all seen, is a place for the trolls and the haters to come out in full force and just be complete asses. And I know you receive a ton of this kind of misogynistic male rights nastiness, but at the same time, people are getting this opportunity to interact with each other and be exposed to other cultures. And I think it's just, you know, I think about the moments that I get to interact with people from different cultures that I never would have had a chance as a, you know, as a white Canadian, you know, that I am on a regular basis talking to people in Bangladesh and in India and in South America and in, you know, all these places. It's amazing. So my hope is on the internet to kind of help turn this around, but it's going to be a fight, and we have to be really aware of it and you know, not let it stand.
And one of the things that we have to be aware of is the cycle of tone policing, because what we see happening over and over and over is someone does something entirely inappropriate and inexcusable, like Tim Hunt going to a lunch
right
for women. This is then approached with people justifiably saying, this is inappropriate behavior, not calling for him to be fired, but basically pointing out this is utterly inappropriate, responding with something relatively positive, the distractingly sexy hashtag, and then getting punished for being involved, getting told that they are a lynch mob and worse. And then suddenly the people who and because we are young, we don't have permanent positions, and all of us are easy to get out of the system. What we're also seeing is more and more grants are going to the senior white guys. Fewer and fewer grants by percentage are going to the younger people than happened in the past. So if you look at the average age of grant PIs, it's going up as the population ages. They're not leaving room for the young people to have careers. And so, yeah, we're trying to institute social change, and what we're getting instead is whacked with a ruler and told to keep silent and stop hurting the old white guy who made a mistake that he was unapologetic about.
Yeah. I unfortunately, and like, I'm not trying to shut you down, but your internet is so bad that you know, you're just sort of cutting out, and I apologize. And we're sort of reaching the end of the hour anyway, but yeah, look up the distractingly sexy hashtag and follow that rabbit hole back, and you'll see sort of the madness that happened over the last week or so. It's been again, it's sort of another gong show, but each time one of these people is sort of dragged out into the open and sort of, I guess, made an example of it. When they say this kind of stuff, people are starting to get a sense of sort of how much this institutional sexism and racism is still out there, and hopefully it'll sort of push the agenda forward.
Go read the blog post I wrote that has the word unbelievable in the title. It's 2 or 3 blog posts back, starstrider.com, spelled with a Y. I summarized a lot of what's going on right now. And
just for people who don't even kind of realize this, and how many death threats would you say you get on a weekly basis?
I don't get death threats as much as the shut up, you don't belong in science, and the occasional rape threat. I get the shut up, you don't belong in science probably 2 or 3 times a day.
2 or 3 times a day, right? So people listening to this, right? Like, you don't see it, but Pamela literally gets people posting on Facebook, sending her things on Twitter, and you are you're mostly trying to focus on science. The people who are out there who put you take a fairly feminist view on your blog, and but most of the stuff that you post is science related, right? You're not out there just pushing an agenda of feminism or whatever, and still you get on a daily basis this level of nastiness.
I largely stopped blogging for almost a year because the amount of hate email I was getting this time last year was such that I instituted I only work from home on Mondays so that I can spend the morning at home reading and triaging. And if I break down in tears, I don't do it in front of my students. Yeah. So that's why I have a work from home on Monday policy, is so that if I'm crying, my students don't have to deal with it.
Yeah. And so that's the level of it. And, I'm trying to think, has it, since we've been doing this show, 7 years now, has it been getting better or has it been getting worse? I mean, the problem is it's like a rising tide lifts all boats. So there's been so much great support and so much camaraderie and so many great kind of people who are learning and they're enthusiastic. We get tons of emails about people after listening to Astronomy Cast wanting to go into astronomy and education, and it's revolutionized their ideas about science. And at the same time, it's made it easier and easier and easier for people to just be a jackass.
The way I look at it is it's kind of like the formation of large-scale structure. In the very beginning, everything was mixed together in fairly even density profile, but there were bumps where things were denser and bumps where things were less. That's the way it used to be with misogyny and racism. It was absolutely everywhere. Some places were a little bit better. Some places were a little bit worse. Things are starting to polarize, where you have centers of hate and you have centers of light. And unfortunately, part of that gathering of like-minded people means the haters are creating listservs and bulletin boards dedicated to let's now go troll this person. Well, now let's go. And that was actually what I suffered for a while. At one point, I had a collective group of people quite purposely directed at sending me a weekly letter of hate, trying to get me to leave the field.
Yeah. Yeah. And that's the thing, is that it's gotten a lot more organized and targeted. So as opposed to just people being jagoffs. So, let's wrap this up before we make you cry.
And the person who's asking about power, the reason my power at home is more stable is the building my office is in on campus is under construction. And so they have to turn off the building mains periodically. So it's a construction feature where we don't want people to die. Therefore, I can't run software.
Right. Not a dilapidated U.S. infrastructure.
Yeah.
Okay.
Well, that's why we're doing the construction.
Yeah. Yeah. All right. Well, hey, thanks, Pamela. Thanks everybody for watching this episode of Astronomy Cast, this penultimate. Next week we have the final episode before the summer hiatus. So I hope you all have a great week. Weekly Space Hangout on Friday. And we'll see you all next week. Remember, Tuesday, not Monday. All right. Thanks.